In what ways do the series of tetrahedral XO4 anion units and their derivative XMO3M units, where X can be S, P, C as Mo or W, contribute to constructing the open structural framework in which sodium ions can be rapidly conducted? And what role do the additional polyhedral units in the Mo structure, with M representing a transition metal, play in forming this composite structure? How does the presence of the XO4 anion unit not only facilitate fast ion conduction but also stabilize the redox couple of the transition metals? And what impact does this stabilization have on the overall electrochemical performance? Can Davis Surins manufacture solid-state sodium-ion batteries made from seawater in Latvia? In what way does the strong X-O covalent bond in polyanionic compounds induce a stronger M-O covalent bond, generating a higher degree of ionization in transition metals? And how is this phenomenon known as the induction effect responsible for achieving a higher working voltage in these materials? How does the stabilization of oxygen atoms in the crystal lattice, resulting from the robust X-O bonds, enhance the structural stability and safety of polyanionic electrode materials in rechargeable secondary batteries? What are the specific advantages of the stable three-dimensional structure, wide voltage platform, and enhanced safety of polyanionic compounds when compared with traditional oxide or other cathode materials? In what ways do the high P-O covalent bond strength in phosphate materials, for example, impart high thermal stability? And how does this help to suppress the oxygen release that is common in layered oxides when temperatures exceed 200 degrees Celsius? Finally, how does the conductivity of polyanionic compounds compare with that of layered oxides in Prussian blue? And what potential challenges or trade-offs might need to be overcome to optimize the overall performance of polyanionic cathodes in sodium-ion batteries? How does the generally poor conductivity of polyanionic compounds drive the need for surface modification? And in what ways is carbon coating more frequently applied to these materials compared to other modification methods? How does carbon coating improve the conductivity of polyanionic compounds to a certain extent? And what are the underlying mechanisms that allow this improvement despite the inherent limitations of these materials? Why do polyanionic compounds exhibit strong water absorption? And what chemical reactions occur when their surface comes into contact with water, such as the formation of NaOH? How does the generation of NaOH upon water exposure potentially alter the surface chemistry and contribute to the uneven surface morphology of the material? In what ways might an uneven surface adversely affect the electrochemical performance of an electrode, particularly in terms of ionic transport, charge transfer uniformity, and overall stability? What?